Problems 76, 79, and 82 are really all about the idea of limiting reactants. So oftentimes when you have a chemical reaction, you'll run out of one reactant first. And when you run out of that reactant, the reaction stops. We call that reactant the limiting reactant. As I said before, it's the one that you run out of first. The other reactant, the one you'll have left over, is called the excess reactant. So this concept is kind of introduced in problem number 76. In 76, you're given a picture. And on the reactants that you start with 2 molecules of ethyne and 2 molecules of hydrogen. A reaction occurs, and in the end you're left with 1 molecule of ethane, so ethane is your product, and 1 leftover molecule of ethyne, so that was one of your reactants. That leftover molecule of ethyne indicates that ethyne was the excess reactant, because there's some left over at the end. The reactant that's not in excess, the one that gets used up all the way, is hydrogen. So that is your limiting reactant. That'll determine how much product gets formed. We put this concept to work in problem number 79. Now in 79, you're given a chemical reaction where hematite, which is Fe2O3, reacts with carbon monoxide to produce iron and carbon dioxide. And you're given amounts of both hematite and carbon monoxide to start off with. That's a giveaway that tells you that this is a limiting reactant problem. Okay, in general, right, when you don't deal with a limiting reactant, you're only given amounts of one of the reactants. And that's basically what all of the problems have been about up until this point. When you're given amounts of more than one reactant, odds are you're going to have to figure out what the limiting reactant is. And when you have a limiting reactant, all that does is it adds an extra step onto our existing framework. So if you see here, I've drawn this diagram that I've drawn 100 times up until this point in red, where you go from grams of one thing to moles of one thing, and you use molar mass to do that. So I'll abbreviate that, and you can use the mole ratio to go from moles of one thing to moles of another thing, and you can use the molar mass of another substance to go from moles of that to grams of that. All of our problems up until this point have involved this diagram to some degree or another. Our simplest problems involved going from moles of one substance to moles of another, just using the mole ratio. And where it gets more complicated is where we add extra steps onto that. So for instance, if we have to go from grams of one thing to grams of another thing, well, now we've got to do it in 3 steps. All a limiting reactant does is it adds another step onto our existing framework. So before we get to our existing diagram, we have to identify the limiting reactant. Now I know I spelled limiting wrong there. You'll have to bear with me for a second. Okay, because the limiting reactant is what's going to dictate how much product is formed, the first thing we need to do is figure out which of our reactants is limiting. Once we determine that, we can use the amount of our limiting reactant to go from grams to moles to grams and so on. So in number 79, you're told that you're starting off with 25 moles of hematite and 30 moles of carbon monoxide, and you want to know how many grams of iron get formed. Our first step here is determine what the limiting reactant is. You can do this one of 2 ways. Right, one way, which we're going to use here, is called the what if, how much method. Now, whenever you use this method, you want to ask yourself, what if all of one of the reactants reacted? How much of the other reactant would we need? In this case, we ask, what if all of the hematite reacted? How much carbon monoxide would we need? So in this case, we're going to convert between moles of hematite and moles of carbon monoxide, and you do that using the mole ratio. Again, you get the numbers from your mole ratio from the balanced chemical equation. That's presented to you in the textbook. We're told that we start off with 25 moles of hematite. Okay, if we want to figure out how many moles of carbon monoxide will react with that much hematite, we use our ratio, 3 moles of CO to 1 mole of Fe2O3. As long as we set it up right, our moles of hematite should cancel out, and we find out that we need 75 moles of carbon monoxide to react with all of our hematite. We only have 30 moles of carbon monoxide. We don't have enough to react with all of that hematite. That tells us that carbon monoxide is limiting. We don't have enough, which means it's limiting. That means that hematite is going to be our excess reactant. Now that we've identified our limiting reactant, we can use the amount that we're given, right, the 30 moles of carbon monoxide, to determine the amount of product that gets formed. we're going to do that in two steps. We already have the moles of our first substance, moles of carbon monoxide. Next thing we're going to do is go from moles of carbon monoxide to moles of iron. We do that again using the mole ratio. In this case, the balanced equation tells us that ratio is 2 moles of iron for 3 moles of carbon monoxide. Those moles of carbon monoxide will cancel out as long as we have our mole ratio right. Our last step then is to go from moles of iron to grams of iron, and you do that using iron's molar mass. And that's 55.847 grams per mole. We want grams on the top because we want our final answer to be in grams, and we want to cancel out our moles of iron. If you set up your conversion factors right, your answer should be 1,120 grams of iron. Number 82 is a similar problem. It's broken up into 3 different steps. And before you get started, the first thing we actually need to do here is write the balanced chemical equation because it's not given to us by the book. So number 82 asks, lithium reacts spontaneously with bromine to produce lithium bromide. We want to write the balanced equation, and then we'll work with it from there. Okay, so we've got lithium, which is an element. Lithium exists on its own, so we're good here. Li, solid. It's going to react with bromine. An important thing to remember here is that bromine is diatomic. Remember our Honkelbrief, H-O-N-C-L-B-R-I-F. Right, all of those elements appear as diatomic molecules in their standard states. So bromine is Br2 and not just Br. And that's going to affect how we write this equation. Our product, lithium bromide, is an ionic compound. So in order to determine its formula, we have to worry about balancing charges. Lithium has a most likely charge of +1. Bromine has a most likely charge of -1. So we just need one of each to cancel the charges out. After we get the formulas for each of our substances in our equation, we can balance it. And you do that by putting 2 as a coefficient in front of lithium and 2 as a coefficient in front of lithium bromide. Now that we have our equation written out, we can get started. We're told that we have 25 grams of each of our reactants here. So we got 25 grams of lithium and 25 grams of bromine. And the first question, question A, is we're asked to determine what the limiting reactant is. In the last problem, we used the what if, how much method. In this problem, I'm going to show you the ratio method for determining limiting reactants. So in the ratio method, what you want to do is you want to compare the ratio of what you have, the mole ratio of reactants that you have, to the mole ratio in the balanced equation. So the first thing we need to do is we need to figure out how many moles of both lithium and bromine we have. And you do that just using molar masses. We're told we solve for that using molar masses, and we end up that we have 3.60 moles of lithium and 0.156 moles of Br2. If we want to set that up in a ratio, right, we can put Br2 on the left and Li on the right, like we have over here. Okay. It makes it a lot easier to compare ratios when you always have the number on the right compared to 1 of whatever is on the left. So we can get it so that there's 1, in this case, mole of bromine on the left by dividing both of our sides by the number on the left. So we're going to divide both sides by 0.156. What this new ratio we have tells us is that for every 1 mole of bromine we have, there are 23.1 moles of lithium. This is the ratio of what we have, so what we actually have. The balanced equation, right, if we look at the coefficients in the balanced equation, it tells us that each mole of bromine will react with 2 moles of lithium. If we compare these ratios to each other, our number for lithium, 23.1, is much higher than the number in the balanced equation. What that suggests is we have excess lithium. If we have excess lithium, then our other reactant, bromine, is limiting. In this case, bromine, therefore, is limiting. Now that we've determined what our limiting reactant is, Part B asks us to figure out what mass of lithium bromide will be produced in this chemical reaction. So we've got our limiting reactant. Now we're going to go through our diagram, right? That diagram that's drawn above. Luckily for us, in the ratio method, we actually already calculated the moles of our limiting reactant. So we can figure out how much of our product will be produced in 2 steps. We're going to go from moles of our reactant, bromine, to moles of our product, lithium bromide, and then go from moles of our product to grams of our product. We need the mole ratio, and we need lithium bromide's molar mass to do this. So first step, moles of Br2 to moles of LiBr. Our balanced chemical equation tells us that each mole of Br2 that gets consumed will produce 2 moles of LiBr. We want our lithium bromide on the top and our bromine on the bottom, so that our bromine will cancel out. If we stopped here, we'd end up with the moles of lithium bromide that will be produced. don't want that. We want grams. So we need one more step, and that's to use the molar mass of lithium bromide. We want grams on the top and moles on the bottom because we want our final answer to be in grams. We want to cancel out the moles. If you set up your conversion factors correctly, your answer to this should be 27.1 grams of lithium bromide. Part C asks us to figure out what the excess reactant is and basically we want to figure out how much of our excess reactant will be left over when this reactant finishes. We can use the law of conservation of mass to help us out here. We know that the total amount of our excess reactant, what we started out with, needs to equal the amount of the reactant that reacted, so that got consumed, and the excess, the stuff that's left over. We can rearrange this to show us that the excess reactant, the amount of excess, is equal to the total minus the amount that reacted. We can figure out how much reacted using our limiting reactant, bromine, and the mole ratios and molar masses we figured out earlier. So what we're going to do is we're going to start with the number of moles of our limiting reactant because we know that's going to be completely consumed. We can use the mole ratio from our chemical equation to go from moles of bromine to moles of lithium, our excess reactant. That tells us that there are 2 moles of lithium for every mole of bromine. Our moles of Br2 cancel out. If we stopped here, it would tell us how many moles of lithium react. We want grams, so one more step. We got to use the molar mass of lithium. We want grams on the top and moles on the bottom. If we solve this equation, it'll tell us that 2.17 grams of our lithium will react. We start with 25.0 grams. We can figure out how much is left over by taking our starting amount and subtracting the amount that reacted. If we do this, we get 25 grams minus our 2.17 grams. We end up with 22.8 grams of lithium left over. And that's it for problem number 82.